Today we're going to be revising the whole of electromagnetism. Now this is both an incredibly important, a really interesting topic in A-level physics, and is naturally split into two sections. First off, we're going to have a look at magnetic fields, which covers the magnetism part. Then we're going to be seeing how they relate to electric fields via Faraday's law. Well, let's have a look at magnetic fields initially. So let's have a look at this fantastically drawn picture of the magnetic field around the Earth. The Earth actually seems to act like a big bar magnet, as if there was a big bar magnet on the inside of it. Notice how we have the North Pole here and the South Pole here. So several very important rules become apparent once we look at a magnetic field. The first one is the magnetic field lines always go from north to south. For instance, here is a magnetic field line. It starts off from the North Pole, and you can see that it curves back into the South Pole. Our second rule is that the arrow represents the direction at which a free North Pole would move. For instance, if I had a free North Pole around here, this has still not been observed, by the way, a free North Pole. So if you were to find a free magnetic monopole, what it's called, you'd probably be awarded a Nobel Prize. But theoretically, if we had a free North Pole, then that free North Pole will spiral, well, not quite spiral, but will follow this magnetic field line back to the South Pole. If we had equally spaced and parallel lines, then this would indicate a uniform field. For instance, in this case, I have some equally spaced parallel lines, which would mean that over here we would have a North Pole somewhere like that, and down here we would have a South Pole with some uniform field between them. There are several patterns that we need to remember. Firstly, if we had two opposing poles, then the field pattern would be similar to this. It can be approximated as being uniform between the poles, but remember the field lines will always go from north to south. If I had two opposing magnets or two opposing poles of magnets, the field pattern will look like this. Remember that all of the field lines will be aiming to go towards the South Pole, so they essentially are going to be carrying on until they find a South Pole along this direction. Okay guys, up next is the magnetic field around a current carrying wire. So remember the magnetic field around a current carrying wire. Let's say that we have a current I flowing through this wire over here, will be concentric circles. And this will be an excellent time to remind ourselves of this very important notation. If I have a circle that has a cross, remember this is like the back of an arrow, and this would indicate that the current is going into the screen or into the page. And if I had a circle with a little dot in the center, this would indicate that the current is coming out of the screen or coming out of the page. A very useful rule of thumb to remember is that if your current is going into the screen, then the magnetic field around it will be a concentric circle that will be going in the clockwise direction. Otherwise, if we were to reverse the direction of the current, so if the current is coming out of the screen, in other words, if we were to reverse the direction of this current, then the magnetic field direction will also change, and the current will now be going anti-clockwise. Another way of remembering this rule is via the right hand grip rule. But just before we do that, let's take a moment to appreciate my drawing over here. This would be an excellent opportunity for you guys to smash that like button. So the rule is that you imagine gripping a wire, and then if your thumb points in the direction of conventional current, then the curve of your fingers shows the direction of the magnetic field lines. For instance, if the current is going upwards, we also have the thumb pointing upwards. The field is then, as you can see, as we have drawn underneath, follows the direction of the curve of the fingers. So the magnetic field lines will be going in the same direction as the curve of the fingers. A couple of common mistakes. It's the right hand grip rule. So this is really important. You're going to get the opposite result if you use your left hand. So you need to use the right hand. Additionally, pay particular attention that this is a conventional current, and conventional current will always be flowing from positive to negative. We can make a little problem to actually test our understanding of the right hand grip rule. For instance, quite a typical problem would be simply to have a wire like so, and let's just draw one wire. Let's say that the direction of the current is upwards. I'm going to give you 2 points, let's say A and B, and a typical question might ask you to state the direction. So state the direction of the magnetic field at, let's say, A and then B. So at A and B, the magnetic field will be following the right hand grip rule. So you can imagine essentially gripping the wire with your right hand, similar as shown over here. And then you're going to see that the field, you're going to have to imagine it coming out of the screen and then going across from A to B and then into the screen at B. So at point A, the field will be coming out of the screen like so, and that's the symbol that we tend to use that, so out of the screen. If you're doing this on paper, it will be out of the page, and at B, it will be into the screen like so, so into the screen. You could use those two rules to essentially draw out the field or the magnetic field around the solenoid. Please pay attention that the magnetic field inside of the solenoid, so in this region here, can easily be assumed to be uniform. So this is really important, assumed to be uniform like so. The North Pole is around here, and then the South Pole is here, and notice the direction of the currents, which will lead us to determining the direction of the North and the South Pole. So if the current is going downwards, essentially right over here, the North Pole will be in this direction. If the field is going upwards, the South Pole will be here. Then if the current switches direction, the poles will also be reversed. Okay, now it's time to look at the force on a current carrying wire. So imagine that you have some sort of an external magnetic field of magnetic flux density. Let's call that magnetic flux density B, some sort of a magnetic field, which is this region over here. And we also have a wire of length L inside of this field. Now, if we have no current, nothing will happen to the wire. But if we were to have some current running through it, I don't know, maybe we put this wire in a circuit of some sort. So maybe we have a little resistor like so, and then we connect it to a little power supply like so. Now there's going to be current going from the positive to the negative terminal. So there's going to be some current moving along here. Those electrons will start moving because there's going to be some current I that will be going through this wire. The wire will actually experience a magnetic force, and the magnitude of that force will be given by the following expression: F is equal to Bill sine theta. Now in this case, F is the force, B, this is our magnetic flux density. So let's write this down, magnetic flux density. In a way, this is a measure of the strength of the magnetic field, and this is measured in the unit Tesla. I, this is just our current, our standard current, which is measured in amps. L is going to be the length of the wire, so that's just the length of the wire measured in meters. And theta, that we use the sine of, or sine of theta, this angle here is the angle between the wire and the field. So in this case, we could say, let's say that the field is perpendicular to the wire. So for instance, it could be, let's say, into the board, or let's say that it's moving in this direction. So there's a couple of very, very important tricks with this equation. First off, when is this equation a maximum? So F is equal to Bill sine theta is a maximum when theta is equal to 90 degrees. This is because sine of theta would then be equal to 1. And in your GCSEs, you would have learned F is equal to Bill, that equation, and this always assumes the field is perpendicular to the wire. The force will be 0 when theta is equal to 0 degrees, 360, etc. In other words, when the wire is parallel to the field, there will be no force, and this is really, really important. So now we know how to calculate the magnitude of the magnetic force using F is equal to Bill sine theta. However, we still don't know how to determine the direction of this force. For instance, we don't really know whether this arrow here is pointing upwards or whether this arrow here is pointing downwards. How can we determine the direction at which the magnetic force acts? Well, for that reason, we need to revise Fleming's left-hand rule. And once again, let's take a moment to appreciate my drawing and hit that like button. First off, I know it sounds really obvious, but it's really important that we use our left hand for this rule. So we're going to use our left hand. The force in our Bill equation is given by our thumb. So the thumb gives us the motion or the force on the wire. Our first finger, also known as our index finger, gives us the direction of the field, and our second finger gives us the direction of the current. For instance, we could apply Fleming's left-hand rule to this example. Now, what I want you to do now is to take your left hand and then apply this. Remember, the way we apply this to our problem is the following. You're going to have to try and imagine this in 3D. The current is your second finger, the field is your first finger. So your first finger should now be pointing directly into the screen. And if you do that, you are going to see that your thumb will be pointing directly upwards, which is the direction of the force that's acting onto this wire. Now that we have looked at Fleming's left-hand rule, let's have a look at charged particles in a magnetic field. So imagine that you have a positive charge, such as this one. You can see that it's positive once again. And let's say that this positive charge enters a magnetic field. Now, if the region of the magnetic field or if the field direction is directed into the screen, so the field is going into the screen, we can apply Fleming's left-hand rule. Because this is a positive charge, the direction of current will be from positive to negative. In this case, this will be to the right, so the current is going to the right. The field is going into the screen, so if we apply Fleming's left-hand rule, there's going to be a force which will be acting upwards. But hang on a minute, this positive charge is already going to the right, and if the charge was initially going to the right and suddenly we have a force which is acting at 90 degrees, well, this would actually be a centripetal force. Remember, a centripetal force will always be acting at 90 degrees to the direction of motion, and the force and the motion will always be perpendicular. It will always be pointing towards the center. So what will happen to this charge is that it will actually start to curve within the region of that magnetic field. The reason why it starts to curve is because the magnetic force is acting as a centripetal force. So we can set the two equal to one another, and we can say that mv squared over r, which is our centripetal force, is going to equal to Bill, which is our magnetic force. So what we can do now is rearrange for our radius of curvature. So what we're going to do is, first of all, use a slightly different, or modify a little bit, our Bill equation. So let's just do that up here. Because we know that F is equal to Bill, then because our current is defined as the rate of flow of charge, so it's going to be Q divided by T multiplied by L. We know that L over T is actually our velocity, so this is equal to BQ multiplied by V. We often write this as QVB, which is another expression for the magnetic force that's acting on a single charge. Okay, well, let's write this in here. So mv squared over r will be equal to QVB. And what I'm going to do now is I'm going to rearrange for the radius. First off, we can cancel out one of those v's, and what we're left with is that mv is equal to qb, and I'm going to bring the r across like so. Finally, I'm going to rearrange for the radius, and this will be equal to mv divided by qb. And this is a formula that you guys need to remember how to derive in the exam. Remember, anytime you have a charge which is essentially moving in a circle in a magnetic field, we could set the magnetic force QVB equal to mv squared over r. Remember, there are two formulas for the magnetic force. One is that F is equal to Bill. The other one is that F is equal to QVB, and we could easily go from one to the other. Okay, next up for revision is magnetic flux. Now, magnetic flux is the product of the magnetic flux density perpendicular to an area and the area itself. So remember, magnetic flux density, so I'm just going to underline that here, this quantity is just B. So what we need to find is the component of the magnetic flux density perpendicular to an area. In other words, it's going to be just this component over here, like so. So let's say that the angle here is theta. The component which is perpendicular to the area will be given by the adjacent component. So this will be cosine theta. In other words, B cosine theta. The magnetic flux is given this Greek letter phi, and the magnetic flux is defined as the product of the magnetic flux density, which we said was B cosine theta. Let's write this a little bit more clearly. So B cosine theta multiplied by the area itself, which is A. Now this is commonly written as phi is equal to BA cosine theta. And this is really, really important, that theta is the angle between the field lines and the normal. And this is so important that I'm even going to write this down. So theta is the angle between the field line and the normal. So quite a common mistake would be for people to indicate that theta is this angle here. This is not true. It is the angle to the normal. Because our equation is that the magnetic flux is equal to BA cosine theta, we're going to have maximum magnetic flux when the field is perpendicular to the area. So in this case, the field is perpendicular to the area, and here the field is parallel to the area, which will be leading to zero magnetic flux. Mathematically speaking, we could use the fact that here the angle between the normal and the field lines is zero. Remember, theta is the angle between the field lines and the normal, and here they are parallel. So in this case, phi will be equal to BA times the cosine of 0 degrees, which is equal to BA. So our magnetic flux will be equal to B multiplied by A. In this case though, the field line is parallel to the area, which means that it's perpendicular to the normal. So remember, in our equation, phi is equal to BA cosine of theta. Theta is the angle between the normal and the field lines. In this case, it's equal to 90 degrees. So phi, our magnetic flux, will be equal to BA cosine of 90 degrees, and cosine of 90 degrees is 0, which means that our magnetic flux will be equal to 0. We can test our understanding of this question with this really simple example here. Find the magnetic flux through this area if the magnetic flux density is 3 milliteslas and you're given the various different dimensions for the area. Okay, well, let's do that. So we're looking for the magnetic flux, so we're going to use phi is equal to BA cosine of theta. Now the first thing I'm going to do is just draw the normal in all of these problems, which is like so. So if the angle here is 55, so the whole thing is 90, which means that this angle here has to be 35 degrees. Okay, well, let's do some calculations. B, our magnetic flux density is 3 millitesla, so that's 3 times 10 to the power minus 3. Our area is 3 centimeters by 5 centimeters, so it's going to be 3 centimeters is 3 times 10 to the power minus 2 multiplied by 5 times 10 to the power minus 2 multiplied, so this together is our area, multiplied by the cosine of 35 degrees. Putting that into a calculator, we are going to get 3.7 times 10 to the power of minus 6 Webers. By the way, just a quick reminder about units. The unit for magnetic flux density B is the Tesla, and the unit for phi, the magnetic flux, is the Weber. It's always good practice when we're revising to work out some base units. So for instance, let's work out the base unit for magnetic flux density. So I'm going to write down an equation for it. So I'm going to write F is equal to Bill sine theta. I'm going to assume that theta is equal to 90 degrees, so sine of theta will be equal to 1, so I'm just going to be using F is equal to Bill. Okay, well, first off, let's rearrange for B, so B will be equal to F divided by IL. Now our force is in general equal to mass times acceleration divided by A times L. Okay, well, let's think about the units of this quantity. So meters, Let's draw some arrows actually from the individual units. So mass, of course, is given in kilograms. Acceleration will be given in meters, s to the power of -2. We're going to be dividing that by the units of current. Remember, current is the amp is the base unit. It's also it's a standard unit for current, is the base unit. So that's the base unit for the current. And of course, a meter is the unit for the length. So those guys can cancel out, and what we're left with is kg A to the power of -1, S to the power of -2 for the base unit of the magnetic flux density. Now, because phi, our magnetic flux, is equal to BA cos theta, the cosine is unitless, so the base unit for the magnetic flux will be equal to the base unit of B, which is kg A to the power of -1, S to the power of -2. So that's the base unit of B multiplied by the base unit of area, which is meters squared. I'm going to also define one more quantity, and this is known as magnetic flux linkage. So let's just write this down, magnetic flux linkage. And this is given by the expression of N multiplied by our magnetic flux phi. N in this case is literally the number of coils. So it's the number of coils. Let's have a look at an example. So now we're starting to delve properly into electromagnetism. So far we've mainly been looking at some maths, and we've mainly been looking at magnetism, and we've done a lot of work. As you can see, we've done all of this. Well, let's have a look at Faraday's law. Now, Michael Faraday had this absolute stroke of brilliance when he discovered his law, Faraday's law. So far, we've looked how if we have electric current, that can make a force arise onto a conductor. What Faraday did was the reverse. What he did was he moved a magnet and hence changed the magnetic field in the presence of a conductor. And in this case, this is a copper wire. Let's say this copper wire has N loops or N coils. And what he discovered, to his amazement, that there was an induced EMF. So actually the movement of the magnet was inducing a current within the wire. If you think about it, Faraday really has discovered the generator, which has been incredibly important to essentially the development of civilization over the last couple of hundred years. Now, Faraday's law says that the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Mathematically, we express this as so E is equal to minus delta n phi over delta t. We could also write this as minus delta nba cos theta. Remember, phi, our magnetic flux, is actually equal to ba cos theta. Then I also need to divide that by our change of time, because in physics, anytime we have the rate of change of something, we're dividing by delta t. The minus sign here is actually really significant, and this minus sign is an expression of Lenz's law. Lenz's law actually states, and this is really important, I'm going to circle it over here, that the direction of the induced current is such as to oppose the change producing it. Now, what do I mean by this? For instance, if I have a north pole of the magnet which is approaching this copper wire, then the wire will turn itself into a magnet, and the current will be such so that the wire, which is now an electromagnet, will produce a north pole which will be repelling this north pole. So Lenz's law means that the two north poles will repel, and this is actually a statement of the law of energy conservation, because if they didn't repel, what would happen was, if we moved it towards it, let's say this turned into a south pole, then the magnet would just fly through and energy will not be conserved. I have an extremely detailed video on this, and because this is a revision video, I'm not going to go into as much detail, but feel free to have a browse. In the description you're going to find a link to that video. Now that we have had a really good look at magnetic flux and also Faraday's law, let's have a brief look into the AC generator. So imagine that we have a coil which I've placed in a magnetic field. The magnetic field has the following direction. So this here is our B field that I've drawn in red. If our coil is being rotated as follows, so you can imagine that it starts up here, and then a moment later it's being rotated this way, and then a moment later it's rotated this way, so now it's flat, and then we have it perpendicular to the field yet again. Well, let's think about the angle of the normal to the field. So the normal is along here. So initially we have theta is equal to 0. Now remember, n phi is equal to NBA cosine of theta. So cosine of 0 is 1, so we're going to have our maximum flux right over here, and this is why a graph of the flux linkage, like so, against time for the AC generator will look like so. Initially our flux linkage is at a maximum, and then will be steadily decreasing until the moment when our coil is now parallel to the field lines. Now in this case our normal is here and our field is along there, which means that theta is equal to 90 degrees, and cosine of theta in this case will be cosine of 90, which is equal to 0. Therefore our flux linkage will be 0, and this corresponds to this point over here. Afterwards, theta will be equal to 180 degrees, and cosine of 180 is minus 1. So this will be this point over here, and the whole process will be repeating itself and will be producing current, which is constantly changing direction as our coil is moving. And to this day, this is the method behind producing electrical current. Talking about this graph, by the way, it's really important to have a look at the y equals mx plus c analysis. Now remember, Faraday's law says that our induced EMF is equal to minus n phi, or the rate of change of n phi divided by delta t. So our gradient, this is really important, the gradient of this curve, gradient of the graph, will give us the magnitude of the induced EMF. So it'll be give us the magnitude of the induced EMF. And our final topic of electromagnetism is transformers. Okay, well, how does a transformer actually work? First off, we're going to have a soft iron core, or just an iron core, and then what we're going to need is some primary voltage. So we're going to take a wire, then we're going to loop it around one of the ends like so, and this will be connected to a variable power supply that produces some AC current, which is absolutely crucial. So we want this to be connected to an AC power supply. So let's just write that. So afterwards, we are going to have a secondary coil, which will be along here, like so, that we could maybe just connect it, let's say, to an oscilloscope or to a voltmeter onto the other side. So we can draw in a voltmeter along here. Okay, well, how does a transformer actually work? First off, whenever we have AC current, we have current which is continuously changing direction. Over 50 times a second, the current is going this way, this way, this way, this way, continuously changing direction. When that happens, the magnetic flux linkage that's being created by the electrical current that is changing direction is also changing. Now, hang on a minute. Now, suddenly, I have changing flux around this area over here, which is going to induce an EMF into my secondary coil. I've summarized how a transformer works over here. First off, AC current, as we said, produces a rate of change of magnetic flux linkage. The soft iron core, by the way, is here to link the primary core to the secondary one. It's kind of providing an easy path for the magnetic field lines to follow. So the EMF is induced in the secondary coil by Faraday's law. It's important to note that there's no actual proper physical connection between the currents in the primary coil. I'll just label them that this here is the primary coil and this here is the secondary coil. But EMF is induced in the secondary coil by Faraday's law because the first coil is producing a magnetic field, and that magnetic field is changing, which changes the magnetic flux, which of course produces a rate of change of magnetic flux, which induces EMF in the secondary coil. And finally, let's have a look at the equation that we have for transformers. Now, our equation for transformers says that Ns over Np is equal to Vs over Vp. In this case, Ns is the number of turns in our secondary coil, Np is the number of turns in our primary coil, and Vs and Vp are the respective voltages in the two coils. The current is kind of flipped in this equation, so Vs over Vp will actually be equal to Ip over Is. This is kind of important, or pretty important. Well, why is that? This is all to do with power conservation. So the power in the primary, so P subscript P, will have to be equal to the power in the secondary. Because power is equal to VI, we can say that VP multiplied by IP will be equal to VS multiplied by IS. So what we can do is just simply rearrange for Vs over Vp. So Vs over Vp will be equal to Ip over Is. So if you're wondering where this part of the equation comes from, it's from right there. Okay, folks, well, we've actually covered virtually all of the points of this very, very vast topic of electromagnetism. Well done for revising. Good luck with your revision and good luck with your exams. Thank you very much for watching, and I hope this video was useful.